Good morning. Welcome back. I'm a little sick today, so I'm going to try to speak softly, which doesn't come naturally to me. So I hope I don't start yelling in the middle and regret it later. But can you hear me okay? Can you hear me okay in the back? Okay. We're talking about HMMs today. HMMs are a really fundamental technique that is very, very good for you to know and understand and see where it's useful. It's also probably the most challenging assignment, and the next to last assignment. So you're going to get the assignment today, and you have to implement some part of the algorithms we discussed today. Then you're going to go off on a break, Thanksgiving break. When we come back, we'll have just one Q&A assignment on the remaining topics that we will cover. Okay, so what is an HMM? What is a hidden Markov model? Formally, it is the following set of items. It is a set of states, typically numbered from 1 to n or 0 to n. It is a set of transition probabilities, which we called Aij, and we collect them in a matrix called the transition matrix. Sometimes I will put the bar here, sometimes I will not put it. It means exactly the same thing. And then it relies on the first order hidden Markov, or the first order Markov property, that the probability of the next state depends only on the previous state. So this is why we can capture the entire stochastic rule with these probabilities. If hidden Markov models were, if we were dealing with second order Markov models, what would we need to do to capture the transition dynamics?
Q of p minus 1.
I'm sorry?
Q of p minus 1.
Right, which means that the A, the transition probabilities, would have to have three indices, I, J, K. The probability that if the time at t minus 1, the state was I, and at time t, the state was j, then the next state would be k, right? So we would need, right now we need an n by n matrix. This is n by n. For a second order Markov chain or Markov model, we would need n by n by n. Other than that, other than the fact that the number of parameters grows exponentially in the order, all the algorithms we discuss work just as well for higher order Markov models. And of course, we can also take a higher order Markov model and reformulate it as a lower order Markov model. So one way of doing that is to say that the n by n states of the last two time steps, we'll consider that one set of states. So there would be, instead of having only n states, there would be n squared states. So it's a question of calling the last two time steps as if they were a single time step. Okay, so we have transition probabilities, and then once we are in a state, we typically don't know, when the system operates, we don't know what state we're in, but we see some observable that's coming out of the state. O stands for observable. These observables can be discrete, in which case they can come from a discrete finite set, in which case they would come from O1 through, say, OK. Or they could come from a continuous space. They could come from the real numbers or the positive real numbers. It depends what it is that you're measuring. The form of these distributions will vary. If there are distributions over continuous spaces, they could be anything. It's up to you to decide. Often people use Gaussians or mixtures of Gaussians, but it depends on the domain. Depends on what you believe the situation is. If they come from a discrete space, they would typically be multinomials, which is the most general distribution over discrete items. If it's a multinomial, that means we will need to specify B sub j for O sub k for any k. And if there are big K number of these, that means that the B vector is a 1 by k. and all B vectors together would be n by k. So for the discrete observation case, the transition matrix is captured by an n by n list of numbers, probabilities, and the emission information is captured by an n by number of observables. We're missing one component that I didn't mention last time. I'll mention it now. To fully specify the model, we need to specify how it starts, how the system starts before, what is the initial state, say at time equals 0. And we have several ways of doing that. It all depends on the domain we're trying to model and what's more appropriate. The most general way of doing it is to specify a distribution over the state of the system at time t equals 0. When we do that, we usually use the letter pi. So this would be, I'll call it initial state distribution. State distribution. Pi over, pi I would be the probability that Q at time 0 is SI. Time 0, one second, time 0 corresponds to a time where the system is starting. It is not emitting any symbol, so there's no O0. So it's a way of thinking of the whole process as starting from some state, transitioning and emitting, transitioning, emitting, transitioning, emitting. You can also think of an HMM differently. You can think of it as emitting, then transitioning, emitting, then transitioning, but then you will not start with Q at time 0, you'll start with Q at time 1. So there's a slightly different formulations. There are even formulations of HMMs that are inherently different, where the emission depends not on the state you're in, but on the transition that you're taking. So the emission distributions, the B's, are specific not to a state I or a state J, but to the transition from I to J. That's inherently different because there are n squared possible transitions. There are only n possible states. So that means that you are allowing the system a more expressive power with regard to what is being emitted. You're making distinctions between emission, the emission behavior when you transition from I to J, then when you transition from I to K, and so forth. We're not going to deal with these kind of HMMs. I just want you to know that if you come across them in paper, there are variations. They're still HMMs. They're still hidden macromodels. They're still finite. They're still relatively easy to handle. They're just different variations. William.
To clarify, when you say O sub 1 through O sub k and the number of observables, are you talking about like the number of different values of a single observable variable, or are there different observable variables that are?
Very good question. I should share with you a terminology that would make our life a lot easier. Did I mention to you types versus tokens? Oh, not everybody remembers. So I think your question was, am I talking about types or about tokens? So if you read an article in a newspaper, and it starts with, the Prime Minister said that the Security Council, you have the word "the" twice there, right? If you count words by their occurrences, these are called word tokens. A token is an occurrence of a word or of anything. If you count words by distinct types, distinct values, as in what occurs in the dictionary, the word "the" is a single word type, but it has two word tokens in that sentence. Okay? So the terminology is word token versus word type. Now, this is not specific to words in language. Whenever you have a population of things that can repeat, if you're counting occurrences, you're counting tokens. If you're counting distinct types, you're counting types. Okay? The terminology comes from philosophy. Now, can your question be expressed in terms of types and tokens? Or were you asking something completely different?
Yeah.
Okay. So this is a set, the set of possible values that the observables can take. Okay?
You say the observables. Like
Any observable.
Just 1 thing is emitted or many things are emitted?
One thing is emitted. That was your question? I gave a very helpful answer to the wrong question. Okay. So whenever you see summation, whenever you see indices in any equation, it's very helpful for you to check, do you know, is this summation over types or over tokens? Or when you see something like O sub I, is this I a type index or a token index? It could be either. Unfortunately, we all use these little indices on the right-hand side to indicate both types and tokens. So in the sentence, boy asked the girl, I can say that this is word 1, this is word 2, this is word 3, this is word 4, this is word 5. What is this 4? What is this 3? These are token indices. Okay? There are 1, 2, 3, 4, 5 word tokens in this sentence. But there are only 4 word types in this sentence because the type of this word is the same as the type of this word. It's the same entry in the dictionary. So when you see something like word I, is this an index into the dictionary? In which case it's a word type. Or is it an index into the position in the sentence, in which case it's a word token? Okay, this applies not just to language, as we said. In this set, what I meant was observable types. I was talking about what values this can take. You know, what observables are possible, not what is a particular observable at a particular time. And I was saying, imagine that there are k different observables. Maybe the numbers from 1 to k, maybe letters or something. To answer your question a little more thoroughly, you could emit a multidimensional signal. In fact, it's very, very common. In speech recognition, for example, what is considered to be emitted from a state is a set of several dozen numbers. It's a point in high dimensional space that captures something about the signal. But the B describes the joint distribution in that space. Okay, so this is our definition of an HMM. And then what might we want to do with an HMM? An HMM is appropriate whenever you believe that the system that you are modeling is sequential, typically sequential in time, but it doesn't have to be time. T in our thing does not have to be literally time. Most of the time it is time. Sometimes it is space. But it has to be sequential in the sense that it should have the Markov property, namely that what happens on one side of the sequence is determined only by where you are in the sequence, what happened right now in the sequence, and not on what happened in the previous part of the sequence. In other words, if you convert it to language of time, what happens in the future depends only on what's happening right now in the present and not on what happened in the past. So conditions, to be more exact, conditioned on what happened in the present, the past and the future are independent of each other. This is the hallmark of a Markov property. It's important because it allows us to calculate important quantities efficiently, which otherwise would be exponential number of things that need to be calculated. So you should consider it when you believe that the system behaves in a way that is Markovian, that is finite, there's a finite number of states, and that these states are not observable usually. If the states are observable, then you don't need a hidden Markov model, you can just use a regular Markov chain, which is a lot easier to estimate and to work with. What are the questions we're going to ask? Let me start with using an HMM. Using an HMM means that you have the HMM. It doesn't matter how you got it. It could be that you derived it from data somehow. It could be that somebody gave it to you. It could be that you invented it. The important thing is that you have it. You are not struggling with what the transition parameters are, or the emission parameters are, or the number of states, or all of that. You know the model. That doesn't mean the model is not hidden anymore. That's something I said earlier. It's still a hidden Markov model. I made a distinction between knowing the rules of the world and knowing what actually happens. If I have a fair coin in my pocket and I know it's fair, then I know that every time I flip it, there's a 50-50 chance of getting head or tail, and that they are independent from all flips, right? In a sense, I know everything there is to know about the rules of the world. The rules are stochastic, probabilistic, but they are what they are. It doesn't mean I know what the future will be. I can assign different probability to different things, but I don't know what the future is. The same thing holds here. If you know the HMM, you know the rules of that world. It doesn't mean that you know how the system is going to evolve in time. So it is still an HMM because as the system starts evolving, you don't know what state it's in. You only see the observables. So using an HMM, you're given the model, the fully specified model, and you're given an observation sequence, which I will write with a big O and usually a bar on top of it. There's no difference between having the bar or not having the bar. It's just my notation. I usually like to have the bar there to remind me that it's not a single number. And then what I want to do is to decode the underlying state sequence. And I mentioned to you before that my chance of that I'm not able to do it with 100% guarantee of correctness. I cannot really know what the underlying state sequence is. And if we play a game when you see the state sequence and I don't, and I use an algorithm to derive the state sequence, it doesn't mean that I'm going to be right. I may not even be right most of the time. I may be right a small fraction of the time. But what I can do is tell you what the most likely state sequence is. And I think we discussed the fact that most likely doesn't mean likely. So the decoding problem is finding the state sequence that has the highest of all possible state sequences of that length, has the highest posterior probability of being the right one, conditioned on knowing the model and knowing the observables. The evaluation problem is very similar. It is given the model and given the observables, calculating the probability of the model given the probability of the observables given the model. Why do I say that this is similar to this? I'll start solving this, and then I will find myself using expressions that are very similar to this one. So let me start by trying to solve this. Probability of observables, I'll write them explicitly. Well, start like this. Probability of observables given the model. Let me write it as a summation over the probability of all possible sequences of this type and the observables given the model. Is it clear to everybody why this is true? This is what I see. These are all the possible stories that led to what I saw. I can write this explicitly as summation over all possible q's of the probability of transitioning from my initial state, q sub 0, q sub 1, times probability of seeing the first observable, O1, given that I'm in state q1, times probability of transitioning from state q1 to q2, times probability of observing observable number 2, this is token index, given that I'm in state 2, all the way to transitioning from state t minus 1, so this O goes from 1 to t, into state qt times probability of seeing the very last observable, O sub big T, given that I'm state t. With apologies for the people sitting there. What I'm saying here is for a particular, I pretend that I know Q for a moment, for a particular set of hidden state sequence, I can break it down into a product of transition, emission, transition, emission, transition, emission. In a picture, it would look like this. Here's Q0. Here's Q1. Here's Q2. Here's O1. Here's O2. I start from here. I incur the cost, the probability of transitioning to here and emitting this, then transitioning to here and emitting this. Keep going all the way to QT and emitting OT. These numbers come from the A and B data structures. This is an A Q0, Q1. I can write it explicitly. You don't need to copy any of that. It's all in the slides, and the chances of mistakes there are smaller than here. So let's just follow the logic. This is summation over Q, all possible Qs, of A Q times B indexed by Q sub 1 of O1 times A Q sub 1 comma Q sub 2 times B times A times B and so forth. So we're alternating multiplying A's and B's, and they're uppercase T of each one of them. Of course, we don't even have to alternate them. We can also calculate the probability of this sequence all the way to the end, and then add the probability of these. So we can calculate the multiplication of all the A's and then multiplication of all the B's. But the point is, for a particular hidden state sequence, big Q, it is a matter of multiplying together two T numbers. Right? It's just picking up those numbers and multiplying them. That's easy to do. So they are calculating this takes order 2T multiplications. So did I solve my problem? Did I solve the evaluation problem? I have to do it for every possible state sequence, Q. How many state sequences are there? Can you say the dirty word, exponential? How many state sequences can there be of length uppercase T? N to the power of T. N to the power of T sequences. So the overall computation required is order 2 times T times N to the T. Forget about the 2, but this is not acceptable. A typical value for N is anything from 2 states, HMM, to 100. Or maybe 10 is a more typical value. T, big T, could be small. 5, 10, could be very large too. But N to the T doesn't work. However, we have a way of deriving the correct answer with only polynomial amount of computation, rather than exponential amount of computation. This is not an approximation, it's an exact calculation, and it relies on the Markov property. How many of you are familiar with the kind of algorithm called dynamic programming? So what we'll be doing is exactly dynamic programming, and dynamic programming is useful whenever you have an exponential number of paths, but they all pass through a limited, non-exponential number of intermediate steps. Because then you can add different paths, you can combine them together. If you think about the Markov property, it's exactly what it allows us to do. It allows us to keep track of partial sums of paths from the past up to the present with only a finite number of intermediate values. So we will be summing implicitly over an exponential number of paths, but we will do it only with a polynomial number of steps. And the way we do that is with a recursive calculation that we keep track of in a table. It's called the alpha table, alpha or forward table. First, I'll define for you what alpha means. Alpha at time t of state I is defined as the probability, according to our model, of observing the sequences from O1 through O sub little t. So this is a prefix of the full sequence. It's observing only up to point little t. And at time t, being in state I, conditioned on the parameters of the model. Again, you don't need to copy it because it's all in the slides and in every paper about HMMs, but stop to just appreciate what it means. It tells you, it doesn't give you the probability of the entire the entire observable sequence, which is what we really want, but it gives you a probability of an initial subset of it. And we're going to use this initial subset to calculate the extended subset, extended by one more. So we're going to build a table here. Here's t. It's going to start with 0, 1, go to t minus 1, t plus 1, all the way to big T. Here are going to be our states. Let's say we start counting from S0, S1. The general case is Si through Sn. I will write above the time here the observables that are related to it. 0 does not have an observable, but 1 does. So O1, O2, O t minus 1, O sub t plus 1, and here's O sub big T. These are the observables we have to account for. This is the evaluation problem. I'm going to show you how I initialize the table, and then how I fill the columns from left to right. I'm going to fill every column from left to right. First, how do I initialize the table? This is in a sense up to me. In the general case, what I put here is that initial distribution, initial state distribution there, pi. Very commonly, people choose that the initial state distribution be very simple, very degenerate. One state is designated as the initial state, and the system is put into that state. In that case, if the initial state, let's say this is the initial state, then you would have 1 here and 0 everywhere else. You don't have to choose to do that. It is part of your modeling decision. Often people look at the states in the system, and then they add one more state that is not part of the normal behavior and say, this is the initial state, and from here everything goes out. They might do that also with a finite state. Some phenomena make sense to have an initial state and a final state. If you think about speech, speech has a beginning, a middle, and an end. When you start, there's silence, there's no acoustics. This could correspond to the initial state. And when you finish also, there's also silence. Or you can determine in initial state, a different initial state distribution, in which case you'd have a distribution here. But this is the initialization. Now let's look at the recursive part. Let's say we want to fill state I You want to fill the value of alpha sub t of state I. Look at the definition of alpha sub t at state I. It's accounting for the probability of the substring up to and including t and being at this state at time t. To be at the state in time t, I ask myself, which state did I come from in the previous time steps? And the answer is I could have come from any of one of these states. So I could have been here, and this is alpha sub t minus 1 of state 1, or alpha sub t minus 1 of state 2, all the way to alpha sub t minus 1 of state n. I'm sorry, this is state 0, not 1. So 0, 1. If I came from this state, I had to incur the cost of transitioning from state 0 to state I, and then emitting the symbol OT. If I came from this state, I had to incur this cost. So these are all associated with transition probabilities A. So from this I can derive my recursive formula that alpha sub t of state I can be calculated as a sum over alpha sub t minus 1 of any state j, when j goes from 0 to n, times transitioning from state j to state I, right, from this j, this is the state j that I'm indexing over, into state I, times being in state I and emitting symbol O sub t. Now that multiplication will happen regardless of what state we came from. So we can put parentheses here. You don't have to memorize it, and you don't have to write it down, but it would be really nice if you understood it, if you understand where it comes from. If I know the alpha values for the entire column t minus 1, I can use them to calculate the alpha values for any cell in column t. I'll do it for all the cells, and then I'll move next to t plus 1, and so forth. So I'm going to fill this table. Question?
So this is only really nice if you have like your pure starting distribution is like degenerate, and then you have 1, because then you have like a base state. But otherwise you would still have to like move over all the states, all the starting state, possible starting states, and like do this whole process for every single starting state, right? Because your base case could be any of the starting states.
I'm not sure I understand why. Suppose this was not degenerate. Suppose there were actual numbers here. You come here, and you calculate this guy based on all these. The exact same formula. Okay? When we fill the table, go back to what we were trying to determine. We were trying to determine the probability of the entire state sequence. How do we read that probability from this table? At the end? I'm sorry?
The last column.
Last column, very good. The entire last column. Because P of O, given the model, can be written as sum over all possible states where I'm being here, P of O and the time t we're in state I, given the model. I goes from 0 to n. The probability of seeing this observable is equal to the probability of seeing this observable and being in this state or that state or all the other states. So just summing all of these. And this is exactly alpha sub big T of I. So if I sum over it, I have the number I want. If in addition, if I impose the further condition that the model must start in an initial state and must end in some final state, let's say the final state is S sub n, final state, then I will read my answer only here. You could impose an initial state without a final state. You could impose a final state without an initial state. You could impose neither, you could impose both. They're independent decisions. Imposing an initial and a final state basically says that any state transition that did not start in the initial or did not end in the final is not a legal state transition. So it's taken out of the calculation. How much computation is involved in getting the answer this way? N times t, how did you get to that?
You have to do a cell for the whole matrix, and the matrix is n by t.
So you have to fill the entire matrix. So you have to fill n by t cells. How much computation is involved in each cell? The formula for each cell is order n computation, some here. So overall we have O of n squared times t. Compare that to what we had over there, which is t times n to the power of t. There's a big difference. N squared is doable. You know, even n of 100, n squared is still doable. Typically n would be smaller than 100. The most important thing is the dependence on t is linear. This is linear in the length of the sequence. That's quite remarkable. Linear in sequence length. This is called the forward algorithm, or the forward table, the forward calculation, alpha table. I don't think it's called alpha algorithm, but good enough. The slides that I posted on the course website have a very nice pictorial depiction of how this table gets filled for a very miniature example with only two states, one of them designated initial, the other one designated final, and only two observables. I think A and B or something like that. So it's really useful for going over specific examples and seeing how it works. Now, before I leave the evaluation problem, let me specify that I can actually solve the problem. Instead of going from beginning to end, I can solve it backwards too. I can calculate, use the same first order Markov chain, or first order Markov property to derive the same answer by starting from the back and going to the front, starting back in time, starting at the end. I'm going to do it for you, not just because it's fun, but because it's going to be useful for us in the next thing we're going to do. I'm going to define a beta instead of an alpha. That's going to look very similar to alpha, but it's going to be different from it in a critical way. My beta of state I, time t of state I, is going to define as the probability not of an initial substring, but of a final substring from some point on. The probability from O t plus 1 through O big T, conditioned on at time t plus 1 being in state I and the model. Compare this definition of beta to this definition of alpha. They are similar and almost symmetric, but they're not quite symmetric. Yes, alpha goes from the beginning to a point, and beta goes from a point to the end. But first of all, the index of alpha is t. It goes up to and including t. Whereas here, with the index t, it starts from t plus 1, not including t. It goes to the end. The second important difference is that here, the condition of a time t being in state I is part of the probability. It's to the left of this line. Here, the condition is to the right of this line. It's conditioned on being in that state. Why do we do that? There's no deep reason for it. We're going to use the alpha and beta calculations together, and we designed the alpha and beta definitions such that they will fit together very well. So they don't cover the same territory. They cover complementary territory. But I could have done it the other way around. I could have defined the beta this way and alpha that way. That would have worked fine too. I'm going to fill a beta table exactly the same way. T, O, 0, 1, 2, all the way to big T, O big T, O1, O2. Here I have S0, Sn. It is most convenient for me if I define an initial state and the final state. If I define this as the final state and this is the initial state, then at time t, I can put a 1 here and zeros here. If not, I have to specify a final distribution. In other words, I think about this as a time reversible chain, which it is. Those of you who study physics know that most of physics, or a large amount of physics, is time reversible in the sense that the formulas, the fundamental formulas, say, of Newtonian mechanics work just as well if you replace t with minus t, if you observe it in reverse in time. So the same thing is happening here. The dynamics of an HMM is time reversible. That means it's symmetric with regard to flipping the time axis. Yeah?
Beta table would be same as alpha table for that observable sequence?
The beta table would be, no, I don't think the beta table would be the same as the alpha table. I don't think so. I think there would be some transformation of the probabilities, but the behavior on the surface would be the same. Yeah.
Why the last column was filled that way?
Because I chose to define the model such that all state sequences must end in this final state. It's an arbitrary decision on my part. I chose it because it's easier for me to show you now how I filled the table. I'm going to fill the table backwards, just like I filled the alpha table forward. So I'm going to use this column to fill this column, and then use it to fill this column, and then this column, and so forth. And I won't spend the time on it. I'll just say this is t, this is O sub t, this is going to be beta of t, a time of state I, and I'm going to fill its value by saying that it will be a sum very much like this sum over the betas that are in the next column over to the right, times the transition probabilities here, times the probability of emitting this symbol. It's all in the slides. The important thing is that logically it's very, very similar to the alpha table, only going backwards in time. And I will read my answer by summing everything here, unless I insisted only on initial state, in which case I will read my answer here. So the simplest symmetric case is when you insist on an initial state and insist on a final state, in which case you will read the answer of the forward table here, and you will read the answer of the backward table here. And these numbers will be identical, because they're both computing the same quantity, just computing it in different ways. The amount of computation in calculating the beta table is identical to the alpha table. It's n squared times t. So we solved the evaluation problem in polynomial amount of time, in fact linear in the length of the sequence, and we solved it twice. We solved it two different ways, both getting the same result. Now I'd like to go back to the decoding problem and show you how similar it is actually to the evaluation problem.
Can I ask a question before that?
Yes.
Just a very quick question. Can you give some concrete example that when will we prefer to use the alpha table method and when will we prefer to use the beta table?
I think we would normally prefer to use the alpha, the forward, because it's more intuitive to go forward. The only reason you need both is because when we go to the learning algorithm, which we'll probably not get to today, they don't do the forward-backward in the assignment, right? I think we dropped it. You don't? Okay, I think you don't. When we go to the forward-backward, maybe I'll cover it very briefly, just in case, then you need both tables. They're useful. Just wait, we'll get there. Okay, decoding problem is find the argmax of P of Q given O in the model. This is our decoding problem. To remind you, you're given the model and you're asked what is the most likely state sequence given that you know the observables and the model. I'm going to play a little trick here. I'm going to write it as argmax over Q of P of Q and O given the model. Divide by P of O given the model. Is it clear to you why this is true? P of O times P of Q given O equals P of Q and O, always conditioned on the model. Now I'm going to observe that the denominator actually does not have Q in it. So I can erase it. So I just converted it into an argmax of the joint probability P of O and Q. I write them in different order, it doesn't matter. I hope I didn't lose you here. I'm saying that whatever maximizes this also maximizes this jointly. I basically allowed myself to move the O to this side. What is this jointly? I could, the naive way, I can say argmax over all Q's of, what is this probability? It's that long sequence of two T multiplications. A from Q0 to Q1 times B of Q1 of O1 times A times B times A times B. Remember that? It's out there, yeah. Now, look at the similarity. When I was trying to do the evaluation naively, I was doing the same thing here. I was going over all possible hidden state sequences and multiplying this A times B times A times B times A times B, but I was summing them. Here, I'm not summing them, I'm looking for which one is the maximum one. So the difference is between summation and maximum. I can write the evaluation problem as, I'll remind you, the evaluation problem, eval problem, is sum of the exact same thing, sum over Q, of Q0, Q1, times B, A Q0, Q1 times B times A times B Exactly the same thing as above here. The difference is here I'm summing, here I'm taking the max and figuring out who has the maximum. So this is to convince you that computationally it's a very similar problem. If you have a large number of numbers and you sum them, it takes the same amount of work, order the length of the sequence to sum them, as it is to find the maximum. So I'm going to solve this problem. If I were to solve it the naive way, it would be exponential number of sequences. I can't do that. But I'm going to solve it using the exact same algorithm. Except in the crucial moment, instead of summation, there will be a maximum operation. So this algorithm is called, when you apply it to decode, it's called the Viterbi algorithm. This is named after the person who invented it, who might still be alive, for all I know. I think he's, I'm sorry? Andrew Viterbi, I think he was an information theorist. And the table, instead of being called the alpha table, is called the Viterbi table. And the recursive quantity, instead of being called alpha, it's called Vt for Viterbi. And Vt, or Viterbi, of time t of state I is defined as, I'm actually not going to go for the argmax, I'm going to go first for the max. I'm going to calculate the max, but I'm going to keep track of what gave me the max so I can get the argmax. Viterbi of state I should be identical to the alpha calculation. It would be sum over max over all states I goes from 1 to n of Viterbi of state t minus 1 of state, that's j, of state j, times a transitioning from I to j, from j to I, times probability of being in state I. What did I do here? This is I, and I'm going from j to I. So this is from j to I. Okay, so I'll do the same thing here. This is I. I'm going from j to I, and I'm here in state bi observing t. Take this, and I can put brackets here. Why do I keep brackets here? Because you can do it in summation, but in this case, the maximum would be the same regardless of this point. Right? Because this does not involve j. So compare this formula to this formula. The only difference between them is that here there's summation. And here there is a max. In fact, when you write the code, it would be the identical code. If you first write the code for the forward algorithm, there would be a sum operation. And you will replace that sum operation with a max operation. With one other caveat, we don't just care about the maximum, we care about argmax. We want to know who gave us that maximum. So, one second, when we fill the Viterbi table, let me draw it here. When we fill the Viterbi point here, state I, and we consider all the j's we could come from, we find the maximum of all of these things going over j. When we find it, we put the maximum into here, but we also keep track of which state the maximum came from. we put a reverse arrow to here that says it came from here, from this state. And of course, this state already has, in our calculation, already has an arrow to the state it came from and the state it came from. So we can follow backtrace and reverse arrows through time to give us the entire sequence that gave us that maximum. The question that you had here?
Are the two indices intentionally different? Like that's a j equal to 1 and that's j equal to 0?
No, not intentional, I'm sorry. It's as simple as, do you start numbering your states from 0 or from 1? Thank you. So the Viterbi algorithm is pretty much the forward algorithm with one line that used to do sum replaced by two lines. Do a max and keep a record of where the max came from. And this solves the decoding problem in time that is quadratic in the number of states and linear in the length of the sequence. Just like the forward algorithm. Order n squared times t. I strongly encourage you to go to the slides. Well, you'll have to for your assignment, but read over the examples there. What I'm trying to give you is more the hand waving, which I'm famous for. The equations you'll have there. So we solved the decoding problem in time linear in the length of the sequence, which is quite remarkable. So now if somebody handed you an HMM and handed you some observable sequence, you can tell them what is the most likely hidden state sequence, and you can do it in a reasonable amount of computation. Remember that the most likely state sequence is not necessarily a likely state sequence. If the state sequence is of length 100, the chances of the most likely one being the right one is extremely small, typically, unless all the mass is concentrated. Now that's if somebody handed you an HMM. What if you are the modeler and you're trying to build the HMM yourself? The first decision you have to make is how many states and how they're related to one another. This decision is typically made by your domain knowledge. This is called the structure of the model, and we will see it in other machine learning formalisms. There's structure and then there's parameters. In the case of an HMM, the number of states and how they're connected is the structure, and then the parameters are the transition and emission probabilities, and also the initial state distribution. Structure is very hard to learn from data. We'll talk about it a little bit. Most of the time we don't learn the structure from data. We bring it as a bias. We bring it from the outside as our belief. The structure in the case of a neural network is the topology of the network, how many units and how they're connected. Suppose you settled on a number of states and you settled on how they're connected. The two most common ways in which we use HMMs is either as fully connected set of states or as left to right set of states. Fully connected means, let me start a new board since it's a new topic. Fully connected, the example of the tunnel that I gave you is fully connected. 3 states fully connected. Every state can go to every other state. Another very common topology for HMMs is left to right. That typically captures phenomena that not only the observables are moving in time, but also what is happening in the system internally is something that kind of progresses over time. So speech is a very good example of that. If you take sound like ba and you want to model it with an HMM, you would break it down literally into the sub-phonetic components, events that happen within milliseconds. So there's the period of silence when I'm building pressure in my mouth before I release it. You don't hear anything, but it is a state of the system. And then there's a moment where I allow that pressure to come out of my lips with the b, and there's a moment of turbulent flow there, because there's a lot of pressure that comes out at once. And then the turbulent flow becomes slower flow, more laminar flow, and and then there's the vowel. So you can describe, if you're an acoustician, if you're an expert in speech sounds, you can describe it as a sequence progressing in time of states, and you can design an HMM that will correspond to each one of these. There could be 3 or 4 or 5 or more intermediate steps, and they are connected to each other, but they might be of different length, each one. So if you're measuring the sound in units of length of, let's say, 10 milliseconds each, you might spend multiple time steps in each one of them. So you may need self-loops here. This is a typical left-to-right HMM. There are variations. You can decide that some events might be skipped over, in which case you will also include links like that. You can design any HMM you want, but it should match the domain in which you're using it. Once you settled on the structure, on the states and the connectivity, you need to somehow estimate or derive the probabilities, mostly the transition probabilities and emission probabilities. You also need to decide on whether you have an initial state or a final state, and if you don't, what is the initial state distribution. These are less important because you would typically be basing your estimation on a very large amount of data, so initial conditions won't matter that much. So let's focus on transition and emission. So the learning problem, HMM learning problem, is given n, which is the number of states, and the topology or connectivity, which in the most general case is everything is connected to everything else. That can always express all the other topologies by setting some of the transition probabilities to 0. And given an observation sequence, I'll call it again O1 through O big T, but this time T is very large. Time T is usually very large. If decoding is done on sequences of length 5 or 10 or 50 or 100 or 1,000, learning might be done from sequences of millions. How long does the sequence need to be? Well, if you have, let's say, 10 states, you're trying to learn transition probability matrix of 10 by 10, that's 100 parameters. And you're also trying to learn the emission probabilities, that's 10 distributions over some observables. So you use that, you go backwards from that to say, this is how many parameters I'm trying to estimate, how much data do I need, right? There's no clear rule, but you certainly need more data than parameters. One data point per parameter typically will not do. That long sequence might not in practice be a single long sequence. It could be many, many shorter sequences that you concatenate together. And technically speaking, the algorithm would work even if you didn't concatenate them, if you started from scratch every time. But for simplicity, we're treating it as a single sequence. So even though the notation is the same, big T, think about it as a very different big T. This is a lot of data. This is moderate amount of data. Yeah.
If you don't, if you concatenate them, isn't that changing the initial state distribution?
Yeah, absolutely.
So that's negligible.
Usually it's negligible. You have to ask yourself. So we use HMMs, for example, for part of speech tagging. So you would have a state that corresponds to the beginning of a sentence, before the first word, and end of sentence. And it turns out it's the same state. It's the sentence boundary state. So you pass through the sentence boundary. So you have to look at the specific domain, but you're completely right. If you concatenate them, there's some things that's happening in the boundaries that you have to worry about. So now you're given the topology and a long observable of many small ones, And your goal is to derive sum A and B, transition and emission. What do you mean by sum? You want a good one. You want a good model. What is a good model? A good model is the model that will give high likelihood to real data and lower likelihood to not real data. The model that assigns high probabilities to things that actually happen. Also a model that results in good decoding. Because once you settle on the model, that's how you're going to decode. Another way of saying it is you want to estimate parameters of the model from the data. Equivalently, estimate or fit these parameters. What estimation method did we learn in this class? Maximum likelihood, yeah. Maximum likelihood is our go-to method. Whenever we don't know, we go to maximum likelihood. It's a very, very general method, and it's got some decent properties. So let's use maximum likelihood estimation. But let me at this point pause and say we don't have to. You can think of other methods for estimating the parameters. For example, if what I care about is not having the best model in some abstract sense, but creating the best decoder, I can try to optimize my parameters so that they are do the best job of decoding sequences, make the fewer mistakes in decoding sequences, and that would lead to a slightly different, somewhat different, maybe not so slightly different value of the parameters. This is called discriminative training. So let's think about it. Let's just add in parentheses. Alternatively, I could use discriminative training. I apologize for this, but discriminative training is an alternative to maximum likelihood training that tries to directly optimize some classification task, some discrimination task. You can think of decoding as a classification task because there's a finite number of hidden state sequences. It's a very large number, but still finite, and you're trying to choose one of them. So just store it somewhere that we don't have to use maximum likelihood, but we are going to use maximum likelihood. When I introduced maximum likelihood, I gave you an example of estimating the probability of a head in a coin. And the way we derive the estimator there is by writing down the likelihood function, simplifying it, taking a log, simplifying further, taking a derivative, simplifying further, solving, and getting a closed form solution. This will not be possible here. We can write down the form of the model, the requirement. I'll write it down right now. The maximum likelihood estimator is defined as the argmax over all possible models of the probability of the sequence given the model. That's it. That's the maximum likelihood definition. This is given. It's fixed. This is what we're searching over. But this is a very large space to search in, right? It has as many dimensions as there are parameters in the transition and emission probabilities. I could try to write this explicitly as using the evaluation problem. I can try to write it as a sum of over all possible Q sequences of P of Q and O. And I can write each one of these as 2t multiplications. I could do that, but then I'll get stuck. I will not have any analytical way of deriving the value of the transition and emission probabilities. So instead of solving it analytically, I'm going to solve it iteratively. I'm going to show you in the remaining 4 minutes, I'm going to show you a iterative algorithm that starts with some value of the parameters and uses some combination of the forward and backward table, the alpha and beta table, to improve the estimate. Now, it'll take a lot more than 4 minutes, so I'm not going to show it to you now. You see it in the slides, and I will go over it again on Monday. But let me do hand waving. You can do hand waving in 4 minutes. We will start with what if. What if this sequence was given to us with the labels? If we were given also this hidden state sequence that's parallel to it. What if we had not only O1 through OT, but also Q1 through QT? Suppose we had that. We had the labels. We had the hidden state sequence. Then what would be the maximum likelihood estimate of Aij? So I write it like this. It's the Aij estimate, that's a hat, maximum likelihood. Can you derive it analytically from these two parallel streams? Assuming they're very, very long. How would you estimate the probability of transitioning from state I to state J? Go back to the tunnel. You are in charge. You have the data of the tunnel. The state of the tunnel is this sequence. The observables are the arrival times, or trip times. Yeah?
How do you see that exact transition?
Exactly. It's the relative frequency. So it would be the count, but how many times you saw state I transitioning, or Qi, Q sub I, transitioning into Q sub J, divided by the count of how many times you saw state Qi transitioning into anything. And the reason I write it like this is, remember that if this is Q sub I, the very last one, we don't count it because it didn't have a chance to transition into J. This is, I'm sorry, this is not the Q's, it's the S's, right? We're going here over states. Si transitioning into Sj versus Si transitioning into anything. So it's the relative frequency, the number of times that we were in state I, how many of them we followed up by being in state J? What about the beta? Beta, say J, of OK. Let's say that this is a discrete output OK. The estimate, maximum likelihood, can also be written down as the relative frequency. How many times we were in state J, count of how many times we were in state J, and of those, count how many times we were in state J, and the observable was K. How many times in this sequence we were in state J? State J. And of those, how many this particular output was this one? So it's a simple matter of counting and writing a fraction. Now, you have to be careful about zeros. Yeah, if some of them are zeros, you have to smooth them. But in principle, the maximum likelihood answer is right there. You do not need anything else. This is not just theoretical. In the real world, many times, you have the privilege of having fully labeled data when you create your HMM. And if you do, you don't need to go to the algorithm I'm going to show you next time. You can just use relative frequency estimation. It's very simple. Sometimes you don't have labeled data, but you can acquire labeled data. You can pay someone to label the data for you. Sometimes it's a matter of just paying or doing the work to do the labeling. Sometimes the actual state is not that well understood, and people may disagree about what the actual state is. So I'll give you two examples. If you're trying to build an HMM for part of speech tagging, for deciding for every word in a sentence automatically whether it's a noun or a verb or adjective and so forth, most people agree. Certainly linguists tend to agree in any case, in any particular sentence, what is the part of speech of every word. But if the underlying states are subacoustic states, in speech, and they relate to the plosive and the explosion in your mouth and the sublaminar flow and all that, then people may disagree. People may not know how to label. So sometimes you can't label the data. But sometimes you can. If you can label the data, I highly recommend you do it, because you get much better estimates that way. What's left to us to do is to come up with a way to solve this problem, the argmax problem, if you don't have access to this, if you only have access to this. And I can tell you that the answer is far from complete, far from satisfactory. You can find a local maximum, but not necessarily global maximum. And it's quite a bit of computation. Please read the slides and the paper that's posted online. It should be very helpful.